This video is just going to talk through the solution to the node classification task in case there's any lingering questions out there about what was done or how. This starts with the boilerplate, just getting things installed and configured. These helper functions are mostly self-explanatory. So here's our wrapper for test, and this is essentially just calling the OGB evaluator object for each of the three data sets, train, validation, and test, to get our accuracies. Characterized performance is considering the distribution on the leaderboard. So for example, if we go over to the leaderboard here for OGB and archive, we see that they give the accuracy average for validation and test, and then plus or minus a standard deviation. So here's the entry for GCN. I record these numbers in the notebook here, but you see there's some natural variation, and this is over 10 iterations. And what this function does here is it looks at your performance in the context of that variation to give some bounds of whether this is in the expected range or not. And basically it's just looking whether your score is within plus or minus one standard deviation. And then I have a convenience function here for plotting normal distributions given an average and a standard deviation, and that's pretty helpful, I think, for seeing the differences in the distributions that we end up getting. And then this get experiment stats is just going to loop through a number of iterations for how many times you want to repeat the same experiment. So here it instantiates the model with the arguments you pass in, and then just runs the training loop and records the results in a dictionary, which can then be used to calculate the statistics. Okay, so the first part you're actually asked to do here is to add self loops and reverse edges to the graph. I played with this problem for a little while without adding these reverse edges, and this makes a huge impact on performance. There's a few different ways you could do this, some more manual than others, but in DGL they happen to have these very simple ways of doing it. Once you have a graph, you can just call the add self loop method, and it will do that for you. And then the DGL package has this function add reverse edges where you can pass the graph in, and that works for homogeneous graphs. And this just checks to make sure that the number of edges are as expected. And then here's the real meat to it. So my input arguments are just the input features, the hidden layer features, the number of classes that we need to predict, the number of layers. I have a flag for adding or subtracting batch normalization layers, which is not really necessary for what's asked of you here. And then there's dropout. So here's our initialization method where we're going to create all the layers that we need. For input, we're going to add a graph convolution layer. So this module list is going to hold all of our convolution layers here. And we have another module list for all of our batch normalization layers. And for the input layer, we add one graph convolution layer and one batch normalization layer. And the dimensionality here is we're going to translate the number of input features to the number of hidden features. And since our batch norm will come after a graph convolution, that's going to need to be the same size as the output, which is the number of hidden features in this case. And then for our hidden layers, of which we will have num layers minus 2, and then minus 2 is because we'll have to subtract one for the input and one for the output. But for the hidden layers, we're just going to add another graph convolution layer and another batch norm layer. And in this case, instead of mapping input features to hidden features, we're going to map hidden features back to hidden features. And the batch norm will have h features as well. And then the output layer will, of course, map the number of hidden features to the number of classes, and then we're not going to include batch norm in this case. So this gives us everything we need, but now we need to stitch together these various layers to do the actual computation. Here we keep h as the variable that's going to keep the embeddings and receive the updates. So the very first H we have, we're just going to assign the raw input features. And then we're going to cycle through all of the layers except for the last one, because the last one gets a slightly different treatment here. But for all except for the last, we're going to pass the graph and the current features in and update the features. So H is going to be overwritten now with this convolution operation being applied. Here we add the batch normalization, and I is going to tell us where we're at in this list. So I take the ith element of my batch norm list. Here I add the ReLU activation function and then drop out. And this will happen for all of the layers except for the last. And then for the last layer, we just do this step. So we take the last element of our convolution list, do the final update, and return it. In other words, we're not applying batch normalization, we're not applying the activation function, and we're not doing dropout on the last layer. And that's it. That's our full GCN implementation, which matches what's given on the leaderboard. We copy the same parameters that I found in their code, which is a hidden feature size of 256 dimensions. These other things are just a property of the data. We're going to use 3 layers here with a dropout of 0.5, and we will use batch normalization. And this is what our model looks like. We have 3 convolution layers and 2 batch norm layers. This is the number of parameters they report on the model on the leaderboard, and that's what we get here. And now we just need to train it. I think they use 1e-2 for their learning rate. I went a little bit lower. And I have an early stop criteria of 50. And if you run this a single time, it'll depend on your random seed, but you get pretty reasonable performance. You should see this validation curve kind of plateau. And if it starts to overfit, then this early stopping will trigger, which in this case, it stopped after 257 epochs. And if you look at the distribution of the leaderboard and compare the performance here, in this case, it says my validation performance is worse than the leaderboard because it's less than 1 standard deviation away from the mean, which we expect to happen in about a third of the cases. So I'm not too concerned about that. The test performance is in the expected range. If they were both significantly lower than the mean, I would maybe be a little more concerned or rerun it a couple times and see what happens. But in this case, having 1 out, 1 in is not that exceptional. So with this, we can go ahead and run the 10 experiments to collect better statistics and plot the distribution. And surprisingly, we actually see that this is doing better than what the leaderboard reports. Not only is the mean higher, but it actually has a lower standard deviation. If we do a simple t-test, assuming unequal variance, we actually get a p-value of about 1%. So there's only a 1% chance that our 10 results came from the same distribution as the 10 that made up the leaderboard. With this, we go on to do some improvements from this bag of tricks paper. The first improvement we ask is for this Loj loss function. I'm not going to dig into the theory of that now, but the relevant formula here is that this Z is your normal logistic loss, or your binary cross entropy. And they're taking the log of Z, but first they're adding this epsilon, and then they're subtracting log of epsilon. Or if you were to expand this out into, substitute the logistic equation for Z, it would expand out to this. But you need to know what this epsilon parameter is, which they actually state up here. They fix it to a constant of 1 minus log 2, and that's because it centers this derivative so that the maximum loss will be right at the classification boundary. I think they have a diagram of this. Yes, here. So the maximum of this is right at 0, which is where the decision boundary is. So we're going to use this same constant of epsilon equals 1 minus log 2. This is our logistic loss, and we don't want it to do an average at this point, so we pass in reduction equals none, so we get a separate loss for each sample in the batch, and then we can do our calculation of from the paper where it's epsilon plus z, taking the log of that, and then minus this log of epsilon. And then we can take the average across our batch and return that. So there's our modified loss function. All we have to do to get that is to pass it in to the train arguments. Here I used a slightly higher dropout. I don't think it actually matters much. I was just playing with different things. And in this case, it says that the validation and test performance are in the expected range. So we go ahead and collect our statistics, and we see that it's actually slightly better than our previous run, although the variance is higher. It's clearly, I think, better than the leaderboard, but it's kind of unclear whether it's any better than our GCN that we just ran. So not sure that Loge is actually giving us much above what we already had here. But compared to the leaderboard, the p-value is very close to 0, and an improvement of around 0.4%. Okay, now on to the linear skip connections with input dropout. I think input dropout is self-explanatory. With the skip connections, the paper gives this kind of straightforward equation. So we have our normal message passing operation here of GCN, where we have this degree matrix inverse root multiplied by the adjacency matrix, and then by D inverse root again. And then that multiplies our features, which then multiply the parameter matrix. So that's our normal GCN layer here. The difference is that we also take our input features and apply a linear projection and then add that too. And the idea here is there's kind of a skip connection that your raw features are going to be included even after your GCN computation, which will help prevent this over-smoothing effect and maintain this information that's in the raw features by continually pumping it into the signal. So this will look very similar to our previous GCN, where we have our layer containers again, module list, one for the convolutions, graph convolutions, one for the batch norms, and one for the linear layers. So now for our input layer, we're going to apply our dropout. So we mentioned in this doc string here that we should use no more than 10% dropout. So we have this minimum of 0.1, and whatever you pass in here, it'll take the smallest of these things to make sure we never exceed this 0.1. But with the input dropout out of the way, we're going to do the following recipe of graph convolution, batch normalization, and then a linear layer. And it's not going to exactly flow like this, but we're going to need one of each of these for all of our model layers except for the output. So similar to before, we'll loop to number of layers minus 2. We'll again add convolution, batch norm, and linear. I'm using bias equals false here, and that was to match the code that I found from this paper. And then for the output layer, we're going to have convolution and linear, but not batch norm, just like before. And then the argument for why we're using these different parameters, sizes for inputs and hiddens, is the same as before. But of course, our first layer needs to handle the number of input features and map it to the hidden size. All the middle layers go hidden to hidden, and then the final layer goes hidden to number of classes. So that'll give us everything we need in terms of components, and now in the forward method, we'll specify how to use them. So the first thing we do is we apply input dropout. So we assign in feet to H. So this is our input features. We then apply dropout to H. Now we cycle through our layers. First, we pass this H through our convolution. So we're using I to indicate the layer number. So we're pulling out the ith convolution layer, passing in H. And then we're going to give this a different name. Whereas before we just updated H directly, now we're not ready to do that because we need to add in this linear piece as well. So we're going to call this C to represent the convolution output. And then we want to take the same H that was passed into the convolution and pass it into our linear layer. So H has gone into two different things without changing. It's gone into our convolution operation and it's gone into our linear operation. So now we have these two separate outputs and we can add them together to form H. So to just bring up the paper again, this is the, so here we're using X instead of H, but that's being plugged into this graph convolution layer. And then it's being separately plugged into the linear layer, and then the result of those two operations are added together. And that's exactly what's done here. And as long as it's not the last layer, so I is less than number of layers minus 1, we'll throw it through the batch norm, the activation function, and the dropout. And if it is the last layer, then this will not evaluate, and we will just return this raw sum between the two terms. And that's it. Now we can pass in these same arguments. We also use the load loss function here. We run it. This says that our performance for validation and test is better than the leaderboard. That's the first time we've gotten that. If we go ahead and collect our statistics, we see that we get yet another improvement. We still have pretty high variation. Maybe this is coming from the load loss function. I'm not sure. I haven't tried it without that yet. But we're definitely seeing an improvement over both our GCN and over the leaderboard by a more substantial margin. So the test accuracy improvement is now around 0.6%. Well, that's it for this video. I hope if there was any confusion that this cleared it up, and I look forward to seeing your extra credit contributions.